All right, this is Mr. Jern, and I'm going to discuss the answers to Workbook 1A Displacement. This one starts off with Angela running to the bus 15 meters away, shown in this little diagram here. Make sure that you always read the scenarios and read every little thing that there is that they have written about a question, because one of the most common mistakes a student does is to answer a question that they think is the question, but then they may or may not realize it, but they didn't read the question carefully enough, and they're actually not answering the question that's being asked. They're answering the question that they assumed is being asked. So don't make that mistake. Take your time, read every little detail about the question. Don't make assumptions. So in this case, we're talking about using representations. In part A, the diagram to the right, it wants you to label Angela's position with 0 meters and label the position of the bus door 15 meters. Label the marks between Angela and the bus with appropriate position values. So all you had to do was start with Angela at 0, and every little dash there, every little hash mark is 1 meter until eventually you get to the bus door, which is going to be 15. Then, based on the labels along the axis in the diagram above, what direction should be labeled positive? Now, because Angela is, the numbers are increasing in the positive direction, then we call that direction positive. Okay, it's to the right, it's toward the bus, whatever you want to describe it as, but specifically in our case, we're labeling that as the positive direction, and that's going to be important. So remember that there's in one-dimensional kinematics, a positive and a negative. So moving on to part B. If the positive direction was labeled as the opposite direction of what you chose in part A, think about how the location for the labels for 0 meters and 15 meters would change. Relabel the diagram at the right with the positive direction pointing in the opposite ways in part A. Include position values along the bottom of the scale. So basically what it wants you to do is say, nope, we're not going to start with 0 being where Angela is starting at. We're going to label 0 as where she's going to end up, the bus. And in this case, the positive direction also switches direction because it is going from 0 to positive 15. And that's going to be important because in the future, we're going to be looking at these types of scenarios, and the exact same scenario is happening in both part A and part B, but where we decided to label 0 changes how we describe it and how we talk about it. So in part A, Angela is running in what we would call the positive direction. And then in part B, we're saying Angela is running in what we would call the negative direction. And that is going to be very important. And it looks on the surface like, well, what's the difference? Well, it depends on how you want to frame your question. So this is just kind of a setup, a prelude to things that we're going to be doing in the future. All right. Part C, you are asked to make a claim about the physical meaning of Angela's displacement in part B. Fill in the blanks below to complete the claim, evidence, and reasoning paragraph. One thing that these workbooks are very helpful for is getting you used to the language of AP Physics and the types of questions you're going to be asked on the AP test, on the FRQs, and the multiple choice questions as well. In this case, they want you to make a claim, right? And they talk about displacement. Displacement is one of those words that you have to know. Displacement is essentially, it's how far you are from where you started and in what direction. Okay, it's going to include a magnitude, the numbers. It's going to include the unit of the magnitude, and it's going to include the direction. So in the evidence, it says when Angela gets to the bus, her position is 0 meters. Again, talking about part B. Angela's initial position was 15 meters. And the reasoning is that here's kind of the definition, or a mathematical definition. Displacement is equal to the final position minus the initial position. Okay, and there's a couple ways we can mathematically represent that. You can say delta x is equal to xf minus xi, or get used to actually saying what the letters stand for. So you would say the change in position, delta x, is equal to the final position minus the initial position. Okay, so read it, but if you keep saying the letters, the X and the F's and the I's, you're not going to develop the intuitive association in your brain with what those letters actually stand for. And that's fine. That's a good way to know what, that's a good mathematical definition. Or probably more for us, or at least I in the class, are going to use this version of the equation, although I feel like there's a typo in the workbook. So I'm going to rewrite it as I believe it should have been written. I'm not sure if I'm mistaken, but I'd never seen it written quite like this. Basically, the change in x, delta x, the change in position, is equal to the current position, as noted by just an x, current position, minus, and this is how I've always seen it, x naught, naught meaning 0, and that just means your initial position. So we have our displacement, delta x, is equal to the current position minus the initial position. Okay, so that is the reasoning there. The claim, therefore, Angela's displacement is 0 meters minus 15 meters. 0 is where she is when she gets to the bus door, minus the 15 meters, and that equals negative 15 meters. So her displacement is actually a negative 15 meters. All right, notice we have the magnitude, the 15, and the units. And the negative is actually indicating the direction. So we have our MUD, magnitude, unit, direction, for when we give answers that involve vectors, magnitude, unit, direction. And that negative is the direction, more or less in this case. Part D, how does the displacement in part C compare to the displacement in part A? Well, they're going to have the same magnitude, but opposite signs. In part A, she is starting at 0 and moving toward 15. And in part B, she's starting at 15 and moving towards 0. Same distance, different direction, all right? Different direction as we defined it. That's important. And in part E, if Angela ran to the bus and back to where she started, what distance would she travel? And then compare that to the displacement. So what distance would she travel is going to be a total. She runs 15 meters toward the bus, positive or negative, doesn't matter. And then she runs 15 meters back to where she started. So 15 plus 15 will give us our 30 meters. And that's the total distance she traveled. Notice that direction really doesn't play a role. I mean, she obviously knows she ran a distance. If you ran that far, you would know it. You didn't run, you don't subtract anything there. You actually just add them together. Basically, you add the absolute values of the distances, the displacements. And then compare that to her displacement. So her displacement is down here at the very last part of the sentence here. It's going to be 0 because if you take her final position, no matter if it's 15 or 0, and then you subtract the initial position, then you're going to get a displacement of 0 meters.